Hi, it's Mr. Kane here, and to the moment we're going to talk about elements, how the atoms are the different elements. Now, back in the days of Democritus and the early philosophers, these four things they thought were the four elements: fire, water, earth and air. But now we know there's a whole lot more. There's actually over 100 elements on our periodic table. They're all atoms, so how are they different? So we've got to somehow tell them apart. We now know that they're all made of the same things: protons, neutrons and electrons. They're all sort of there like that. The protons and neutrons in the nucleus, and electrons whizzing around the outside. So how is it that we have different elements if they're all made of the same things? Okay, they're all made of atoms, all the elements, and they're all made of the same things. How are they different? Alright, it comes down to something called the atomic number. Each element contains a different numbers of protons. So the atomic number of an element is how many protons is in that element's nucleus. So for example, here's some elements on our periodic table. Iodine has 53 in its atomic number, therefore 53, here we go, 53 protons. Lutetium, never heard of that before, has 71. Vanadium, I've heard of that as part of strong metals, an alloy. It's got 23. Well, here's oxygen, we need that one every day. That's got 8 protons in its nucleus. So the atomic number of hydrogen is 1, so all hydrogen atoms have 1 proton. And as we just pointed out, each element has its own atomic number, therefore its own number of protons. So as I said, for oxygen have 8 is their atomic number, so they have 8 protons. Right. Atoms are all electrically neutral. They don't have a charge. So we've got positive protons in the middle, in the nucleus. Therefore we've got negative electrons around the outside. To be neutral, they have to have the same number of each. So the number of protons tells you how many electrons that atom has. So here's a picture of carbon, and carbon is number 6. So in the center of our carbon atom, we're going to have 6 positive protons, and around the outside we've got 1, 2, 3, 4, 5, 6 electrons. 6 positive protons cancel out 6 negative electrons, therefore it is electrically neutral. So the number of pluses equals the number of minuses. Now we come to the mass number. This is actually how how heavy each element is. So the mass is in the nucleus. That's where the protons and neutrons are found. They are the ones that have the mass, so right in the middle, right in the nucleus. And it's the total number of protons and neutrons is the mass number. So if go back to carbon, it's got 6 protons and 6 neutrons, so its mass number is 12. So we've got 6 protons, 6 neutrons, 6 and 6 is 12. The atomic mass is 12. Okay, what can we do with that? So if you know the atomic number and the mass number, you can figure out how much of each bit it's made up of, how many protons, how many electrons and how many neutrons each atom has. So here's potassium, and we have its atomic number up the top here, 19. So that tells us it's got 19 protons and 19 neutrons, and down the bottom here we've got 39. We're going to ignore the 0.98 for the moment, so we'll ignore it over here as well and over here as well. So its mass is 39. So if I subtract the atomic number 19 from 39, I get 20. So therefore potassium has 20 neutrons. So the number of neutrons is the difference between the mass number and the atomic number. If you're wondering about that 0.98, most potassium atoms have 20 neutrons. There's a few that actually have 21. So when they average it out, we get the average number of neutrons is 20.098, but if we just stick to the number before the decimal point, it keeps it simple and it keeps it easy. If you want to learn more about isotopes, stick with the chemistry topic and we'll get more into that later on. So number of neutrons equals the mass number minus the atomic number. Let's have a look at that some more. So we can write down what the atom is, what element it is, all in sort of a shorthand without writing too much, using the symbol and the numbers around it. So here's a section of a periodic table. We'll learn more about that soon. And we've got the symbol for the element calcium. So instead of writing the whole word out, we just put Ca, means calcium. We have its atomic number of 20, and we'll go with 40 for its mass number. So 40 minus 20 tells me it's got 20 neutrons. 20 at the top tells me it's got 20 protons. The charges must balance out, so therefore it must have 20 electrons. Okay. So the atomic number is the superscript, which is the little number at the top. The mass number is a subscript, that's the number at the bottom. Do watch out for that though. I have seen some periodic tables where they've been written the other way around, but most commonly the ones I've been looking at and the ones I try and use have the atomic number at the top and the mass number at the bottom beneath the name and the symbol. Okay. Helium. Let's try this out. It's got 2 there, which is its atomic number, so it has 2 protons. Number of protons equals number of electrons, so it must have 2 electrons as well. 4 is its mass number, so that's the number of protons and neutrons in it. Number of neutrons equals the atomic mass minus atomic number, so 4 minus 2 equals 2, therefore helium has 2 neutrons. And it's one of our lightest gases too, and it's been a star in some movies, and people have actually tried that out for real too, although I wouldn't recommend that. Okay, try one yourself. Gold. How many protons has gold got? How many electrons has gold got? How many neutrons does gold have? I think I'd just rather have gold. So we need some information from the periodic table. So here it is. Here's the symbol for gold, Au. Now sometimes the symbols don't match up with the name because we've used the original name for gold, something called, it comes from Latin, aureum or something like that. Look it up and find out for yourself. There's a few that have the original Latin names rather than the more common names, and that's where the symbols have come from. So we've got some numbers on there. We've got 79 and 97. 79 tells you the atomic number, which is how many protons it has, and therefore that's how many electrons it has because it's electrically neutral. So gold's got 79 electrons. The mass number is 197. This is where some math sneaks into some science. So atomic mass minus the atomic number equals how many neutrons it's got. So gold is 197 minus 79 equals 118 neutrons. Go for gold. There we go. Okay, so all matter is made of atoms. Everything is made of it. You, me, bench tops, computers, whatever we're using, it's all made of atoms. The air we breathe, everything. Atoms, they're the smallest bit of an element that keeps its identity in any chemical reaction. One atom can react with one other atom, and because they've got the same different numbers of protons, so they're each are their own element. So if you've got a pure gold lump in front of you, you know that it's only made of pure gold atoms. So elements are pure substances made of only one kind of atom. And remember, atom comes from that Greek word atomos, I hope I'm pronouncing that right, meaning indivisible. You can't make it any smaller, although we now know it is made of 3 smaller parts. How big are atoms? We looked at that a little bit before with the Astrodome example, but they are really, really tiny. So, for example, a pure copper coin, the size of a 10-cent piece, has got, what's that, 2.4 times 10 to the 22, so 2.4 with 22 zeros after it. It's a huge number of copper atoms in it. There's only, 7.5 billion people on the planet, so 7.5 billion, that's like 7.5 with 9 zeros after it. 10 to the 22, that's 22 zeros, so that's more than a billion, so that's heaps of atoms. There's the coins, 10 cents on the left nearest my wrist and the hand, and these are actually, our 10-cent coin isn't made of pure copper, that would wear out too fast, so it's an alloy, a blend of things, but that's the size of it. So there's a huge number of atoms in that coin, and we can actually see them. We've now created special electron type microscopes that can see it. Scanning tunneling electron microscope involves using a very pointy needle-like device that has a charge on it that can detect the charge on individual atoms, and it scans it and it can create an image, and we can see them. There we go, that's what the image looks like, and that's magnesium atoms, which is the white blobs above boron atoms. So we can't see the bits of them, the protons, neutrons and electrons. We can sort of see a fuzzy outline of what the atoms are, and yeah, I'm not sure if we'll ever get super clear pictures of all the individual bits. So that's elements and how they're put together and what makes each one different from the other, and I hope that's been helpful.